Hello, so today we're going to be discussing electrostatics. Basically, the electric force that exists between a charged object and other charged objects or electric fields. So we're going to start off with discussing Coulombs Law, which is the way that you can calculate the force between two charged objects. So, electric forces. Let's first define this. An electric force exists between two charged objects, and what causes it is the interaction of the electric fields of object 1 and object 2. And as you know from first grade science, like charges repel and opposite charges attract. And if you want to calculate the force between multiple objects, like if you have three, first what you need to do is calculate the force between these two, and then calculate the force between these two, and if you care, also the one between those two. So this is one of those where as you start adding things together, the complexity goes up by a lot. So with 3 or 4 objects, you can do this by hand. If you got lots and lots of charges, for instance, a charge along a wire, or a charge along a ring, or a charge on a flat surface, one of the things that you can do is you can solve it by integration, but this is something that you're going to be doing in AP Physics C or at whatever other calc-based physics class you end up taking in the future. Now, the other thing that you can do is you can have big clouds of electrons or other charged objects. And one of my professors has spent most of his career designing computer programs that'll do simulations of clouds of protons, because as you make more and more charged objects in this cloud, the complexity goes up by a lot. So his whole career has been trying to be able to make better and better simulations of clouds of charged objects, because there's a lot of things in life that use them, like particle accelerators. And for those of you that are going, but Mr. Alley, particle accelerators aren't real life, they're just cool physics, I would say that a lot of things in the medical field are particle accelerators, like all the things that deal with radiation therapy. That not only is particle physics life, particle physics is key to saving lives in that case. But that's me digressing a little bit. So let's talk about how we're going to calculate that, and that's going to be Coulombs Law. So as the strength of the charge increases, so does the electric force. So higher the charge, higher the force. And as with many other things in physics, as you increase the distance, the force is going to drop off by the radius squared. So this is called the inverse square law. And we've seen it a couple of times, but it basically deals with anything radiating off a single source. So we saw this in universal gravitation. We didn't talk about it much, but it's also how the energy of a sound wave dissipates as it goes through the air. As I talk, everything gets weaker as this inverse square as it goes out. And light does the same thing. So there's a light source right there. As the radius increases, the intensity of light falls off by 1 over that radius squared. So combining all of these and a constant just to make all the units work out, we end up with Coulombs Law. Now, if you're looking at this and going, hey, look, this looks awfully familiar, you're right. This is very similar, very mathematically similar to Newton's law of universal gravitation. So rather than gm1 m2 over r squared, we've got k, which is Coulomb's constant, times the charge of object 1 times the charge of object 2 over the distance between those objects squared. Now, there's a couple differences here. In that, in Newton's law of gravitation, you couldn't have negative mass. There's no such thing as negative mass in the universe. If you prove me wrong, you get a Nobel Prize. But you can have negative charge. An electron has negative charge. So how does that work here? Well, a negative times a positive gives you a negative. So that means that electric force is going to be opposite the direction of the radius, or in. And if you've got two positives, that's going to give you a positive answer. So that's going to then make that force be positive, so it's going to be in the same direction as the radius. So it's going to be out. And if you have two negatives, that again makes a positive, so that's going to make that force out. So that's where we get the likes attract. The negative goes opposite the direction of the radius, and opposites repel is because that becomes the numerator is positive, and so the force is going to be in that same direction as the radius. So let's do an example with this. Or first, let's talk about how strong this electric force is. And it is strong. So this is one of those where if you take a balloon and rub it on your head, you can make it stick to all sorts of things, like the TV or the ceiling. But that's a very, very minuscule amount of static electricity. Yet it's countering the entire gravitational force of the Earth. And so this is much, much, much stronger than the gravitational force. In fact, the relative strength of gravity from the other fundamental forces, so that would be electromagnetic, strong and weak nuclear forces, is one of the great mysteries of physics. And one of the things that baffled Einstein towards the end of his career is, why is gravity so weak? We usually don't think of gravity as being all that weak because we experience it all the time. But compared to all these other forces, yeah, gravity is very weak. We just see it on a large scale by a lot because there's no such thing as negative mass, and therefore it all adds up together. So this means that Coulomb's constant is big. Specifically, it's 9 times 10 to the 9th Newton meters squared per Coulomb. It rounds to 9 times 10 to the 9th. It's actually like 8.987, I think. Yeah, so Coulomb's constant is a nice round number. It rounds up quite nicely to 9 times 10 to the 9th, and therefore it makes it easy to remember. So it comes from this equation here. So Coulomb's constant is really 1 divided by 4 pi epsilon naught, where epsilon naught is what's called the permittivity of free space. It's basically how susceptible to a vacuum, or how susceptible a vacuum is to an electric field. And that's something that you're going to be getting onto later in your career in physics. It's not something that you need to know right now. But Coulomb's constant is a really, really important number. So important that it earned itself a cameo in the game Fallout. So if you happen to be playing this, go to University Point, it's sitting there. Alright, so let's now do an example with this. So let's find what the speed of an electron orbiting a proton in a hydrogen atom is. So this is a picture of a hydrogen atom that I stole off of Wikipedia, and it gives you an idea of how much smaller that proton, how small that nucleus is compared to the rest of the atom. So it's 100,000th the size of the rest of the atom, essentially. And this picture also gives me an excuse to talk about that funky looking unit that looks like an A with a halo on top. The Stargate symbol, if you'll pardon my extra nerdiness here. And that's called an angstrom, which is 1 times 10 to the minus 10 meters. So let's think about this. This seems like a central force problem. So let's solve it similarly to what we do with some of the gravitational problems that we were doing earlier. So that force the electric force is going to be our centripetal force. So that's going to be equal to the mv squared over r that we can remember back from before Christmas break. That was a long time ago. All right, so now force electric, we know how to calculate that. That's going to be using Coulombs Law. So we can go ahead and put that in. So the force electric is equal to K Q1 Q2 over R squared. So, and that's going to equal mv squared over r. And we can now solve for v. So the velocity of the object is going to equal the square root of q squared. Why did I do that? Well, we know that the charge of the electron is equal, it just happens to be opposite, to the charge of the proton. Therefore, we know that it's going to be attracting, so we can ignore that sign. So the magnitude, we're just ignoring the signs here, is going to be equal to that charge times its charge again. So that's why I've got that as a q squared. Divide that by the mass of the electron times the radius that it's operating at. And thanks to quantum physics and stuff that you don't need to worry about for a long time yet, we know with very great precision the radius that that electron orbits at. And it's called the Bohr radius, which is 0.529 times 10 to the minus 10 meters. We can now plug all that numbers in, so we can then find the velocity. So this is going to be 9 times 10 to the 9, which is Coulomb's constant, times the fundamental charge of an electron. So this is the fundamental charge, so it's the charge of an electron, charge of a proton. So that's going to be 1.6 times 10 to the minus 19 coulombs. That's, of course, going to be squared. Divide that by the mass of the electron, which is 9.11 times 10 to the 31 kilograms, or negative 31. Yeah, they're tiny. And then we can multiply that by the radius that we found using the quantum physics, and that's going to be 5.29 times 10 to the minus 11 meters. And this all gives us an answer of about 2.62 times 10 to the 6th meters per second. So the electron really is zipping around the nucleus of the hydrogen atom. And as you add more charge to the nucleus, the speed is going to go up and up and up, to the point where when you get up to the larger atoms like uranium, you would now get numbers that are so close to the speed of light that now you need to start figuring in special relativity, but that sounds like a lesson for a future year. With that, I hope you all have the very most wonderful of days.